Better Buildings for Humans is powered by Advanced Glazings, makers of the Solera line of products. Solera is the leading glass glazing made specifically for architectural daylighting and with extreme insulation performance. Learn more at advancedglazings.com.
Hello and welcome to this episode of Better Buildings for Humans podcast. I'm your host, Joe Menchefski, and this is the podcast where we take a look at the impact that the built environment has on our health, our wellness, our productivity, and our general joy of being alive. And of course, we always have to talk about sustainability as well. And on that note, let me introduce you to Denise Martin. Denise, welcome to the show.
Thanks, Joe, for having me.
Oh, it's an absolute joy. This is the first Kiwi, the first New Zealander that I've had on the show, and it's very exciting. So Denise is the CEO or president of BEO?
Oh, well, at the moment it's a one-man band, so I have all the titles.
You have all the titles. You're the boss and the what do they call it? Chief cook and bottle washer, the whole 9 yards.
That sounds about right.
Thank you very much for being willing to talk to me. Let's start, as I always do, by getting to know you a little bit. Tell us about your background and tell us about the path that led you to create BEO.
All right. Well, let's start with perhaps a little bit of my upbringing. So I think in school I already had, the affinity to physics and especially applied physics, and love to ask questions. And by the time the early 2000s came around, I still lived in Germany most of the time. And my then husband and I, we were renovating some properties that we owned in Germany. So in the early 2000s, there was a large push in Germany with upgrading buildings to like specific standards. And that was called KfW over there, which meant that, if you did specific upgrades on a building, you had to basically combine them into a group of updates. And all of those would then lead to, a more holistic benefit for the building occupants in terms of overall performance. So you couldn't just say, for example, change windows out. You also then had to add ventilation, for example, or you then also had to add vapor control with wall insulation and things like that. So it was a very thought through process that I sort of got thrown in as a property owner back then. And when I started living here in New Zealand, I worked with a structural engineer at the time, and the sustainability part became, sort of more and more important in our area of like structural engineering, a little bit with thermal breaks, and sort of passive house was starting to pop up here in New Zealand. And so naturally, I started picking up that side of things with energy modeling. I was given a blower door, which I sort of knew what it was at the time, but I didn't really know how to operate it. But I learned on site, doing the hard yards for years and years. So I've taken blower door testing sort of under my umbrella, and then became a passive house designer through doing the course and the exams and everything, and studied in Dresden for a couple of semesters in applied building science. Yeah, and in 2018, sort of finally the day came where I said, okay, this is a sustainable business in its own right, and basically founded BEO, sort of slowly transitioned out of the structural engineering into, focusing on energy modeling and passive house and offering blower door testing as a service and sort of anything that goes around passive house. So that included thermal bridge modeling and so on. So I sort of got established in that part through passive house here, and it sort of grew from there pretty much.
Okay, just to make sure that we don't miss anything, can you tell me all the services that you're currently offering?
So currently I'm offering passive house certification. So I've become a certifier in the meantime. I still offer passive house design for buildings that want to become certified and need sort of the guidance along the way. With that, I offer the thermal bridge modeling and just general energy modeling using PHPP, because you can, model buildings basically of all performance levels across that, including general compliance here in New Zealand with the building code. and I do blower door testing for residential and commercial buildings. And I've also picked up the training program to train other people to learn how to do blower door testing for residential, and since earlier this year also for commercial blower door testing. So large scale, the building physics that sort of come with testing large buildings and the technicalities of using multiple fans and preparing tests.
Well, let's talk about the mechanics of that a little bit. I don't know it very well, and I'm sure there's a lot of people that know the outcomes rather than the methodologies or the mechanics. So let's talk about specifically air permeability testing. What specific things do you do when you're, passive house certifying to confirm air tightness?
Well, essentially what you do is you are putting a fan into an external door of a building. So if you just think of a building as a box, so somewhere on that surface of the box, you're installing a fan, and that fan extracts air out of the building or pushes air into the building. So you can do it both ways. And that creates a pressure difference because you're blowing air out of the building, so it creates a negative pressure on the building fabric. And then all we do is we basically measure the airflow at certain pressure targets and document that. And then we create a mathematical graph that says at 50 Pascal, which is the target reference, the air of that, or the air leakage of that building is that and that airflow in cubic meters. And then we reference that against either the building volume or the building surface area. So in passive house, you would have heard about the air tightness of the building, which is usually referencing the volume of the passive house because it's all around ventilation. And then the international baseline standard is more around the leakage per square meter of surface area of that building fabric that we're testing.
Okay. All right. So you're literally building an airtight box around a fan to draw air? Yeah. Okay. All right. That's cool. I honestly didn't know that. All right. Let's talk about IAQ for a second. Is there any kind of trade-off in terms of indoor air quality when you have a space that's so incredibly tight, or a home that has such a high level of air tightness?
Yes, there can be. And there is an increasing problem with buildings. Because like back in the days, houses were just leaky by default. Houses here in this part of the world are still very leaky.
Yeah.
But like in Central Europe and Northern America, the air tightness problems, they've sort of gone through these issues like 30 years ago. And yes, air tightness can lead to not just indoor air quality problems, but moisture problems as well if you don't have ventilation. So what we're trying to do with air tightness is to limit the uncontrollable leakage in a building fabric and basically funnel that through a proper ventilation system instead. So that helps with the energy efficiency because you don't have, air leaking in and out of the building, which then your heating and cooling system has to constantly battle. But we're trying to funnel that basically through a ventilation system. And with better air tightness, a ventilation system can actually do better what it's supposed to do. So it has to go hand in hand. And I think that correlation hasn't been understood broadly enough. So this is why you see all the, the different opinions on air tightness. I still, when I post things online about air tightness, still get people who say, as you're suffocating the people inside the buildings. And my typical response is, yes, passive house has killed many people over the years.
The bodies are strewn all over church.
You're basically walking into a passive house that is super airtight and there's only dead people on the floor. But, like you see, there's still like this understanding of, air tightness is problematic. And yes, on its own, it can be problematic. And actually, it will be problematic because we are building better by default. Components become better, craftsmanship, becomes better and more detailed with prefabrication as well. And if you're not looking into your ventilation strategy, you're running into problem very quickly because we create a lot of moisture inside.
Do you want to bring lots of healthy, beautiful natural light in your building and still meet energy codes? Try Solera from Advanced Glazings. Learn more at advancedglazings.com. Right on. Well, since we're talking about moisture, let's talk about condensation analysis. Could you do the same thing that you just did for me with air tightness and explain how you test for condensation analysis?
Sure. So with condensation analysis, that's also a little bit twofold because you have, your indoor environment, which may lead to condensation on visible surfaces. Like, when you've got your cold beer in the summer, for example, you've got the cold surface. So yes, it attracts moisture from the outside to condense on it. And we would typically see that, obviously on windows or especially the window frames if they're metal. And I think a lot of people are quite familiar with that problem. But that's not necessarily the condensation that we should be worried about because it's on the surface and we can see it and we can sort of clean it or ventilate it if we need to. Condensation analysis goes into the actual structure of the building fabric, and we can calculate that using a program called BUFFI, which has been developed by the Fraunhofer Institute in Germany. And it's basically a mathematical tool that allows us to calculate heat and moisture movements through building materials and see if they are accumulating anywhere inside the building fabric and whether there is enough vapor drive or drying capacity in either direction, inside or outside, to perhaps resolve that issue, or whether we need to find other materials or construction assemblies to prevent that from happening. So it's typically when you open a wall and you see mold inside a wall, we can predict that before it actually happens.
Is there a measurement, like a single measurement for a material's ability to transfer moisture, like the equivalent of thermal resistance or electrical resistance? Is there an equivalent for moisture transportation resistance? Yeah. What number is that, or what do you call that?
There's a couple of different ones. It's called either vapor permeance or vapor resistance. So probably similar to thermal resistance and thermal transfer. The same applies for water vapor. So some materials are more resistant to that transfer than others. And there's a gradient, obviously. Not every material is the same. In Europe, we are typically working with an SD value, which means it's like the equivalent air layer thickness in meters. So something that has, like a 0.5 air layer thickness would be very vapor permeable, whereas a vapor barrier, like a foil facing, for example, that would have an SD value of over 1 million meters. So there's, a range from.
Right. Okay, that makes a lot of sense. One more thing. Let's talk about thermal bridge testing since I brought it up. Can you tell me about the methodologies for doing thermal bridge testing in a passive house scenario?
Right. So in passive house, or when you're using any energy modeling in general, you account for thermal bridging two ways. So first of all, you've got, your thermal bridging through timber framing, for example. So you've got like a timber frame wall and you've got insulation between the studs.
Right.
And you typically would account for like the percentage of timber in that area layer as a thermal bridging correction factor. When you're looking at thermal bridging for passive house, you take that even further and you're looking at the geometric changes in the building. So you've got more, say, for example, more exterior surface area in an external corner of a wall. And you would calculate the increased heat flow through that geometric change. Now you can extend that, into materials as well, like if you've got steel in your structure. So if you just account for the percentage, it's not usually as accurate because it's got way more thermal conductivity. So it leaks out way more heat than its surrounding area. And it's difficult to account for that just by allocating a percentage into the material layer. So we can calculate that using different software. There's Therm, for example, is a free software. It's not super user-friendly, but it's doing the job. And then there's more sophisticated two-dimensional software, like I use Flexo. And there's also 3D software, so you can calculate three-dimensional thermal bridges where, not just the geometry, but also components or fixings, for example, can be calculated.
So it's a calculation more than a measurement.
Yes.
We talked about wood and thermal resistance. I normally think of wood as being a highly non-conductive, an insulator, essentially.
Yes.
How much thermal conduction do we actually have through wood? How consequential is that?
It's not, timber is actually really good. It's about 3 to 4 times as thermally conductive as insulation, for example.
Okay.
So, whereas steel, that would be, in the hundreds or thousands times more thermally conductive than an insulation value. So timber we sometimes actually use as a thermal break instead of, insulation products because of, its structural properties. So sometimes it's easier to use just timber opposed to. Yeah.
So mass timber is becoming a very common way of doing structural construction over here in North America. Is that trend similar in New Zealand?
Yes, mass timber has become very popular here. And I think it's based in its embodied carbon. So that trend obviously has made its way here to New Zealand as well, and Australia too. The use of mass timber is fantastic, obviously, because it's a great product to work with. What I have encountered here, however, is that in terms of how you assemble like a wall, for example, is that it's being used a lot like precast concrete. And it's very popular here to insulate concrete on the inside face of. So from Northern America, you'll know that exterior insulation has the benefit that it keeps the structure nice and warm, which prevents condensation issues, especially on concrete surfaces. But here it hasn't been picked up yet. That could be a problem. So when we're talking about, condensation within construction assemblies, it becomes quite important to insulate on the right side of a structure, especially when you're dealing with structural timber that could, where the structural integrity could suffer over time if there is consistent moisture ingress into the structure. But outside of that, it's been very popular. Lots of projects are going up with mass timber here.
Just out of curiosity, how high can you go? I think we're at 14 stories now in Canada. What's the height limitation in New Zealand?
I don't think there's a height limitation per se.
No?
And sorry, I'm not on top of all the latest projects, but I know that I've definitely seen 7, 8 stories. And I think one of the first non-residential passive houses that was certified as student accommodation in Australia was definitely in that sort of 10-story range, but don't quote me on that.
Okay, that's... Yes, I didn't mean to put you on the spot. Forgive me. It was very recently bumped up to 14 in North America, which is the only reason I have that number in my head. It was just announced like a couple of months ago, maybe, or 3 or 4 months ago. So, that new limitation is fairly new. Let's change gears completely. I want to talk about human beings for a little bit. So on your website, you talk a lot about occupant comfort, as much as you do about sustainability objectives, which I love. I mean, that's the reason I have this show. You even go so far, I found a quote on your website where you say that comfort is a basic human right, which I love that. And so in what ways does your testing and analysis predict occupant comfort?
Well, it's actually quite easy because occupant comfort is actually put into not legislation, but there are 2 standards actually that you can use to measure occupant comfort. So in America, we've got the ASHRAE 55, and in Europe, we're using the, I think it's 7763 or something like that ISO standard. But
okay.
It's measurable, and it basically starts with temperature. So there's a temperature range that we humans feel comfortable. You're talking about temperature gradients, like from top to bottom, that we feel comfortable. Like, think about cold feet, for example. Then there's velocity ranges that we feel comfortable in. And then there's obviously the air quality ranges that we feel comfortable in, and that includes CO2, that includes humidity or relative humidity, and it includes particles, VOCs, like all of these things are actually defined. And funny enough, Passive House is designed around this comfort and around, the air quality of buildings. So the target is already there, and there's a reason why people that are living in passive houses can experience this kind of comfort that, most people in normal buildings cannot automatically achieve if those things are not put in place, and the things are having adequate insulation for the climate you're living in, looking at the solar heat gains, the ventilation design, and so on. So it's quantifiable. And I think that's, when we're looking at the technology that we have available today, it's easily achievable across all climate zones.
Okay. Now, have you ever been hired specifically to deal with comfort issues rather than energy management issues where, the primary driver was occupant comfort?
Yes. Yeah, actually
Is it common?
Yes, very common.
Okay.
Most recently here in New Zealand, I would say overheating is a big issue. So what happens, on the pendulum is that houses were extremely cold here for a long period of time. So the pendulum swung from we need to insulate more. So the components got better, the glazing got better, the insulation got better. People just stuffed insulation everywhere. And now we're facing the opposite side of the pendulum where people suffer from the houses being too hot in summer and they can't ventilate, they can't cool it. So we're on the other spectrum of it now. So the overheating issue is currently one of the big ones I'm getting engaged for, to do energy modeling and just look at how they can be tackled in the design phase early on before it leads to issues.
Forget the old paradigm that privacy means darkness. With Solera translucent glazings, architects can design spaces that are private, filled with natural light, and visually stunning. It's time to rethink how buildings work and feel. Learn more at advancedglazings.com.
Right on. Okay, so let's talk about sort of geographically specific issues. And then again, this is just about my curiosity. What would be some of the bigger issues that you face in healthy, sustainable buildings in New Zealand these days? And just to put it in context, if you're in the Middle East, you have to focus on cooling. Where I live in Canada, I mean, right now it's like, I don't know, minus 18 or minus 19 outside. So, the emphasis is on tight houses so that you're not spending so much in energy for heating. Do you have specific issues like that in New Zealand?
Yeah, we do. And the problem is here that we're just on the cusp of being sort of a heating climate. So a large portion of New Zealand thinks we're, in the South Pacific, so we don't need any, heating or cooling whatsoever. So we actually have the problem with moisture and heating at the same time. When you're in a clear, cold climate, then, heating isn't really the biggest problem because all you do is you insulate and, you make the houses more energy efficiency in that way. And yes, depending on how cold it is and how airtight, you have to look at some, vapor properties of wall buildups. In a climate like New Zealand, we have a lot of humidity outside already. And in summer, especially in the northern part of New Zealand, like ventilating into the building can actually introduce more moisture than it actually helps ventilate out, which is really problematic. So the houses are not technically insulated well enough to maintain heat. And then you have, the moisture issues that you're introducing through ventilation. So it's actually a little bit more complex than when you're, looking at really hot climates, for example. The problems aren't necessarily just the cooling demand or the cooling load. A lot of it is moisture related. So mold and all of these things, they lead to real poor indoor air quality and lots of respiratory impacts for the occupants. So like asthma, for example, is a huge issue here in New Zealand. Yeah, and you can't just ventilate that out. That is a real issue here.
Okay. All right, one more sort of, I guess, geographically related question, maybe. Daylighting. Is daylighting a big part of your work? Is it something that, is important to your countrymen, is important to you in your work?
Well, yeah, not as in like daylight analysis, but it is part of some of the rating schemes here, and it's part of the building code that you need to meet certain, daylighting requirements.
Okay.
Personally, in my day-to-day business, I don't do daylighting analysis per se, where say like you need to have this much lux per square meter in your space. It's more the opposite here because we've got all these beautiful views that people basically want to live in glass houses. So it's more about,
Right.
converting people into like framing the view rather than, having the view everywhere.
Right. Yeah. Okay. I gotcha. All right. We've come to the part in the show where I ask my $1 million question, Denise. I ask this question of every single guest, and I ask them to answer it from whatever perspective they like. And the question is, what makes a great building?
A ventilation system.
That's what.
Like when you're asking from
I
the,
should have guessed. I should have guessed. Yes. Go ahead.
yeah, clearly from like the building performance point of view, I would definitely, over anything else, if you can spend your money on anything in a building, get a ventilation system because it basically funnels your fresh air in and out of a building through proper filtration systems. Ideally, it's designed, so it doesn't blow air into your face all the time. It deals with moisture, which we don't automatically do just by opening windows. And, the higher performance you go, the more you think about like heat recovery and so on. But it's the lungs of the building. And if that's anything that makes a building healthy, it's, putting in proper lungs.
I love it. All right. Before we go, do you have any exciting news or anything that you'd like to share?
Yes, maybe, since I alluded to it earlier when we started, the training for the commercial blower door testing is now available, obviously, through my platform and basically walks you through the testing of commercial buildings, the building physics of it, the technicalities of it. So even if you're outside of New Zealand and you want to learn a little bit about that, feel free to stop by. Also run the training course for the residential level blower door testing. And yeah, I've got more courses coming, so always happy.
You have to tell us your website to make sure people can find it.
It's beoscience.com, so BEO for Building Envelope Optimization. That's the original name of the company in one word, beoscience.com.
Perfect. All right. Denise, thank you so much. It was an absolute pleasure, and I learned a lot speaking with you today. I appreciate it. Thank you.
Thanks, Joe. Nice to speak to you too.
We hope you enjoyed this episode of Better Buildings for Humans. For more information on the world's best light diffusing and highly insulating glass glazing, please visit advancedglazings.com.